All right, so lesson 4 is about fusion and fission. And we are going to talk about the different types of radioactivity that chemists are concerned about. There's fusion, there's fission, and then there's radioactive decay. Radioactive decay is something we're going to talk about or be concerned about on Monday. But for now, we're going to just mention the fact that radioactive decay occurs when an unstable atom loses energy via radiation. Types of radiation that it gives off are gamma radiation, alpha radiation, and beta decay. And like I said, we'll spend more time with that on Monday. The two types of radioactivity we're going to be concerned about today are fusion and fission. Fusion is when two atoms combine to form a new atom. So fusion would be kind of like if I took element A and maybe element B, and it combines to make like atom E. Okay, so making something new. Fission is when we take an unstable atom and we push it to become so unstable that it actually can't handle itself and it breaks apart. So into two new atoms. So this would be something sort of like, element L breaking apart into, say, element, maybe B and maybe element G. Okay, and I'm just using random letters here to illustrate the fact that they're not necessarily next to each other on the periodic table. And like I said, we'll really focus in on alpha, beta, and gamma radiation Monday. So let's focus more on fusion today. So fusion, like I've already stated, is when you take two atoms to combine to form a new atom. Fusion is so basically the protons and neutrons in the first atom and the protons and the neutrons in the second atom combine together. They fuse together to create a brand new atom that's stable, and in that process, it produces a lot of energy. So the places that we are aware that fusion occurs is fusion can occur in the sun, I guess more specifically in stars. And it produces lots and lots and lots and lots of energy. And the reason why I went to great lengths to write lots and lots and lots and lots and lots is because fusion occurs in the sun or in the stars. And when it occurs in the stars, it produces so much energy that if we were to attempt to replicate it on Earth, it would be the amount of energy would be so uncontrollable, so great that we wouldn't be able to contain it, and it would basically melt stuff, like everything. So fusion is something that we have been unable to reproduce in a safe manner on the planet Earth. So we generally don't. He said like nuclear bombs, and the answer to that question is not yet.
Wait, so which ones do you...
We're getting there. We're going to get there. I'll do a little spiel about about atomic bombs. Now, with that in mind, so like I said, it's atom A plus atom B makes like atom E or something along those lines. The other thing that's important to kind of think about and or remember is that the protons and the neutrons are combining into the nucleus to make the nucleus of the new atom. So the way that these things are represented is in fusion equations. Okay, and so some things to remember is that think about, I guess, is that the numbers on the left side of the equation have to equal the numbers on the right side of the equation. Okay, So we're going to take a couple of minutes to kind of like explore that a little bit more in detail. So in this example, we have the mass number of this isotope or atom, and we have the mass number of this isotope or atom, and I'm going to add them together. So 13 plus 18 equals 31, which becomes the mass number of my new atom. We also have the atomic number of the first atom and the atomic number of the second atom. And you may recall that that's protons, right, in the nucleus. So I'm going to take 6 plus 9, which is equal to 15, and see that that becomes the new atomic number of my new atom. And then I'm going to get out my handy-dandy periodic table that I've named Jethro. You may have named yours Sven. Maybe you named yours Sarah or Sally or I don't know. Anyway, and I'm going to go ahead and I'm going to locate element number 15 on the periodic table, and I see that element number 15 on my periodic table is equal to phosphorus. So so carbon with a mass number of 13 and fluorine with a mass number of 18 produce phosphorus with a mass number of 31. And that's kind of all that's to it. So we've got some practice. We'll do one or two together. Here we go. Oh, this first one is just like the one up above. So I think I might skip it, I guess. Well, maybe not. I'll just kind of do it quickly. So we got 13 plus 18 equals 31. So I get 31. And 6 plus 9 equals 15. So I get 15. And I check out my handy-dandy periodic table, and I see that's phosphorus. All right, let's do one with one that we haven't done before. So here I have sodium and calcium, right? Sodium, in this case, is a mass number of 23. Calcium is a mass number of 48. So I'm going to take 23 plus 48, and if I do the math right on that, I believe it's 71. So that's going to become my new mass number for my new element that I'm creating. On the bottom, I have my atomic number of 11, my atomic number of 20. So I'm going to take 11 plus 20, and that equals 31. So that's going to go down below. I'm then going to go and locate element number 31 on the periodic table, which, if I found it correctly, is going to be gallium. Element Ga, that's the element that melts in your hand, but not your mouth. Like, you know how M&Ms melt in your mouth and not in your hand? That's their slogan, right? Or it used to be their slogan. Gallium is a metal that if you hold it in your hand, your body temperature is warm enough that it'll just melt into a puddle in your hand. Yes, sir.
So like it's to the top one. Oh wait, never mind. The numbers are switching.
Gotcha. Okay. Now the next one is, I don't know what my first element is, but I know what my product is going to be. So if they have to be equal to one another, here is my product, which is 8 on this side. And so on the other side, those two things have to add up to 8. And I already know that 4 is one of the reactants, so 8 minus 4 is 4. So that tells me I'm going to have a mass number of 4 over here. I see my atomic number is 4, so I'm going to do the same process, 4 minus 2, which gives me 2, so I'm going to put a 2 over here. And I'm going to go to the periodic table and locate element number 2, which happens to be helium. Now in this case, we took 2 helium atoms and we stuck them together and we make beryllium. And that's basically how the sun works. The sun is a giant ball of helium, and that giant ball of helium is combining helium with helium to make like beryllium, and helium with beryllium to make like carbon, and helium with carbon to make like oxygen and stuff like that. So that's kind of how stars work a little bit. So any question about fusion so far? Fission is when we take an unstable atom and we agitate it some more, make it even more unstable, and then it splits into two new atoms. Fission has a tendency to occur in nuclear power plants. And has a tendency to produce lots and lots of energy. But note the difference. The first one was lots and lots and lots, fusion. Fission is lots and lots. So it produces a lot of energy, just less than fusion. This one happens on Earth, like I said, in nuclear power plants in a contained system, but it also happens to happen in atomic bombs. And so the way that it works in an atomic bomb, very, very basic understanding or description, is that an atomic bomb, they'll take an unstable element like uranium or plutonium, and they will give it a seed neutron. So they basically take a neutron and they bombard it with a starter neutron. And that starter neutron takes something that's already unstable and makes it even more unstable. Okay. And then when it does that, it creates a nucleus that just can't physically exist. And that nucleus that can't physically exist is so unstable that it will separate into two smaller nuclei. Okay. And those two smaller nuclei, hopefully, ideally, are going to be stable, but some of them are not. But it also emits more neutrons. And so those other neutrons that it emits go off and run into another unstable uranium atom. And the process is repeated over and over and over again until all of the uranium is used up. I believe in one of the nuclear bombs or the atomic bombs that was used during World War II had something like 64 kilograms or something like that of uranium in it. So that's why it produced so much energy. Now, you'd have to think that a country that is in the process of producing a weapon would probably want to test the weapon before they use it in real time, right? So one of the things that the country that produced the weapon did was it went and found a bunch of voluntold from a local army base and told them to get on a bus. Nope. I mean, I'm not saying Russia didn't do that, but
I think like the largest one, they used it. Russia used it on the island.
I'm not saying that didn't happen. I'm just speaking from our government's perspective. They basically went and they grabbed about 50 or 60 guys and said, hey, get on this bus. You're going to be part of a test. And they took those 50 or 60 guys and they drove them out to New Mexico in the middle of the desert or something like that and told them to stand in a trench. And then they took those 50 or 60 guys and they detonated a prototype of the atomic bomb that was used in World War II. And they basically then went out and collected those guys and then studied them. And most of them survived. Okay. So that's the thing. Most of them survived. And one of them that survived wrote a book or was interviewed or something along those lines. And he stated that, like, when it occurred, so you know how, like, when you're asleep and your mom comes in and like flicks the light on and you're like, it's bright, it's too bright, I can't handle it. When these individuals were part of this test, many of them did what most of us would do, which is cover our eyes like this, right? And when they covered our eyes like that, what actually they could retell was that they could see the bones in their body as if they were like looking at an X-ray with their eyes closed. So it was about the same as turning on a light switch when you're sitting in the dark by yourself. Note the sarcasm. But then those same guys were tested multiple times. Like some guys were only tested once, other guys were tested more than once with other prototypes, and then they decided that they had the right formula, and they went and they used that bomb. So I don't think anybody was like, "Hey, I'll sign up for this activity." I think it was more along the lines of, "Hey, you're going to get on this bus." Just saying. Yes, ma'am. Yes, ma'am. So lots of energy is produced. Lots of energy. All right. So let's talk about how these reactions work. Just like before, the numbers on the left side have to add up to the numbers on the right side. So I'll write that again. Okay. Now, so what I mean by that is I'm going to take a look at the numbers that I have on my left. I want to identify how many total are on my left. So here's my mass number for uranium, and here's my mass number for the neutron that's going to be put into the unstable atom of uranium. So 235 plus 1 is 236, which means that on the right-hand side, everything has to add up to 236. So if I look at the mass numbers, 144, 89, and then 1, right? 144 plus 89 plus 1 plus 1 plus 1 happens to equal 236. Now, the reason why I did 1 plus 1 plus 1 is because there are 3 neutrons. Do you see that? That 3 tells me I have 3 neutrons that are being released. And then my atomic numbers, 92 plus 0 must equal 92. So that means everything on the right-hand side must add up to 92 as well. So 45 plus 47 plus 0 plus 0 plus 0 happens to add up to 92. It did. I can't even blame that on the COVID fog. That's just my mistake. Ooh. All right. So then the next 3 are going to be just practices of this. So here we go. First one looks sort of similar, I guess, to start off with. I've got 235 plus 1 gives me 236. So that means that everything over on this side, on the right-hand side, has to add up to 236. But I'm going to take the subtractive approach on this one because I have some information and I'm not one to like guess. So I'm going to take 236 minus 144 minus 2 minus 1 minus 1. So 236 minus 144 minus 1 minus 1 gives me 90. So my missing situation here is going to be 90. And my protons on the left side is 92 plus 0 for a total of 92. So I'm going to do the same thing on the right-hand side. 92 minus 54 minus 0 minus 0 is 38. And there should probably be a plus sign back here. And so I go to my handy-dandy periodic table that I named Jethro, and I locate it, and I definitely identify that the element number 38 is strontium. Why don't you give the next one a try? Okay. So in this case, we had 236 for the mass number on the top on the left side. We took 236 minus 154 minus 72, and I got 10. But the notation for a neutron is 1 over 0. So I still put a 1 for the mass number, and then I put a coefficient of 10 in front of it. On the left side, 92 plus 0 was 92. So I took 92 minus 62 minus 30, and I got 0. So that was my number of protons for the neutron. And then I still had a 10 in front of it. And do you have a question?
Why do you put the 10 in front?
The question is, why do I put the 10 here? The answer to that question is that the 10 in front indicates the number of neutrons that are released. So technically speaking, there's a 1 here. So just like in algebra class when they say like x plus 2x is 3x, right? In front of an x that's got nothing in front of it, it's a 1, right? And so the same thing applies here. If there's nothing in front of the 235 in front of the uranium, it means that there's just one uranium atom, right? So the fact of the matter is that the notation for a neutron is 1 over 0, okay? Because the neutron doesn't have a proton, right? And that's what the number on the bottom is. So, but the fact of the matter is I still had to account for all of the things. So I needed 10 neutrons. So like in the one up above, I ended up taking 236 minus 144 minus 1 to indicate there were 2 neutrons.
So you move the number over if it's a neutron.
Yes. Well, but Okay, try the next one. The last one. All right. So in this case here, I had 254. 254 minus 108 minus 1 minus 1 minus 1 minus 1 gave me 142. 98 minus 44 minus 0 minus 0 minus 0 minus 0 is 54. 54 is element xenon on the periodic table. Questions about that? Yes.
So for all of them, the last, the last thing always has a number before the fraction. So why is it always just the last one?
So you know how in math class, like 2 plus 3 is 5 and 3 plus 2 is 5? basically, what we're getting at here is that those can technically be in any order, first of all. Second of all, the reason why there's that number in front is because that number is the indication of how many neutrons were released. So if the mass number on the left side has to equal the mass number on the right side, in the case of the middle one, 154 minus 72 was going to be like 226. Right? Or, sorry, Matt, sorry. Yeah. 154 plus 72 is 226. And so I needed to have 10 neutrons. And so that's why the 10 is in front of the neutron notation. Does that make a little bit of sense?
A little bit.
Okay.
In the equation, why don't we do anything with the 4 or the 10, either of the equations?
Like the question is, why isn't there a 4 or a 10 on the other side? Is that kind of what you're asking?
Yeah.
Because the total mass number on one side has to equal the total mass number on the other side. But in this particular type of reaction or equation, the difference is that the number of neutrons. So when we talked about this earlier, we talked about the fact that one neutron starts the reaction by making the original species, in this case uranium, become unstable. When the unstable atom separates into two atoms, those two atoms hopefully are less unstable or more stable. But they also, in that process, end up releasing some neutrons. And basically the neutrons that are left over are the neutrons that are, or the number of neutrons that are released are basically the difference of the new atoms that are made. So if, for example, zinc wasn't produced, but say something else was produced, like gallium, which has which might have a mass number of, say, 71, let's just say, then the number in front of the neutron would be 9. Does that make a little bit of sense?
Mm-hmm.
And this is like super basic overview of kind of how fission works. All right. Any other questions? Ish.